Okay, lesson 5, trig identities. So if we use the quotient identity to show that sine x equals tan x times cos x. So the quotient identity, it's basically if I substitute in for tan x. So again, if I go back to those list of identities that I have on my formula sheet, I have that the left side of the equation equals sine x. It's about as simplified as it's going to get. So now I'm going to look at trying to simplify the right-hand side to equal that left side. So I have tan x cos x. And what can I write tan x as? Sine over cos. And when I multiply these two together, the two cos x's will cancel each other out, and I'll be left with sine x. Okay? So in the next part, the question is this statement true for all values of x? So we can investigate this by looking at the graphs. So what I would like you to do is I would like you to use the graphing calculator, and I'd like you to graph sine x and then tan x cos x. Actually, sine x we should be able to draw without actually graphing it. Remember how we draw sine x? Starts at 0, goes through pi, and then comes back up to 2 pi. And if the two sides are equal, what should tan x cos x look like? It should be the same. So double check it just to make sure that it is the same. So when I go to graph these, what I may choose to do is if I go down to my y2 and I go over to where the line is and press, enter, the line gets thicker so that when I graph it, I can see the calculator drawing both graphs. So here's my sine x, and then here is my tan x cos x. So that again shows me that the graphs are the same. So then the next part of the equation says let's try putting in some certain values. So I'm going to go to my table set. And I'm going to go to ask on my independent, and then I'll go to my table, so second table. And my table's nice and clear. So now I can input values of x and see what the corresponding values of y would be. So the first one that we're asked to do is to evaluate pi over 2. So pi divided by 2. What does it equal in the first graph? So what does pi over 2 equal in the first graph? And what does it equal in the second graph? An error, meaning that it's undefined. So f of pi over 2 is equal to 1. So that's this value right here. And g of pi over 2 is undefined. So let's try the same thing at 3 pi over 2. So if I type in 3 pi over 2, I get that the function f is equal to, and g is equal to undefined again. So f of 3 pi over 2 is equal to -1. That's this value down here. And g of 3 pi over 2 is undefined. So what that means is that I have points of discontinuity. Well, why do I have these points of discontinuity? What is going on in this graph that is causing these gaps? And it says, explain why using the results from A. So if we go back up to A, when we were doing the proof, what did we do with tan? What did we change tan into? Sin x over cos x. So because tan x equals sin x over cos x, if cos x equals 0, tan x is undefined because cos can't equal 0. Well, guess what cos pi over 2 equals? It equals 0. If I look at my cos graph, this was my cos graph. So the minimum point was at pi, and the zeros were halfway in between. So the same thing, cos 3 pi over 2 also equals 0. So I have these points of discontinuity because at pi over 2 and 3 pi over 2, cos is equal to 0, and when I put that in for tan, I get this undefined value. So my graph, if I was to draw it correctly, would have these holes at pi over 2 and 3 pi over 2. And the graph would still look the same as a regular sine graph, except for these points of discontinuity. So really, what we're looking for in this section is non-permissible values. When we are looking at our identities, we need to watch out for these non-permissible values. So we can say that sin x equaling tan x cos x is an identity that has non-permissible values whenever cos x equals 0. And those non-permissible values would be whenever I have pi over 2 plus multiples of pi n. So pi over 2, 3 pi over 2, the next one would be 5 pi over 2, 7 pi over 2, and so on. The holes in the graph may not appear on a calculator of a trig function. If we can use the zoom trig in degree mode, then we would see the holes. But then we're going to have to change all of our window settings and everything else. You're not going to see it in radian mode. But if I look at my window settings, if I went into my table set, there we go. If I started my table at 0, and this delta here, or the little triangle means delta. What does delta mean in science class? Changing. So this is my scale. What do I want to go up by? So if I went up by things like something like pi over 6, which is what we tend to do in radian mode, and then we went to auto, now every x value is going to be a multiple of pi over 6. So 0, pi over 6, 2 pi over 6, 6, 3 pi over 6. There's my first error. And I can keep following it down that way. And then I can get to my next error. So that could be a way that I could use my table of values to help me out. I just have to adjust my window settings accordingly. Okay? So if we look on the next page, it just talks about the non-permissible values of an identity. When you are determining the non-permissible values, there's two areas to focus on. Tangent, cotangent, secant, and cosecant functions will have non-permissible values because all of them consist of a denominator. Tan can be written as sine over cos. Secant is 1 over cos. Their non-permissible values are whenever cos is equal to 0. Cotangent, which is cos over sine, and cosecant, which is 1 over sine. Whenever sine is equal to 0, I have a denominator that's equal to 0. So that's the first thing, is whenever you see your reciprocal trig functions and tan, you're going to have a non-permissible value because within that secant, I have a denominator. Within cotangent, there is a denominator when I look at its equivalent form. And then if there is a denominator anywhere else in the identity, there would also then be another non-permissible value. Non-permissible values can also be called restrictions. In many of the examples, the restrictions are what your solutions for sine equaling 0 or cos x equaling 0. And then they've even gone through and reminded you. Sine x equals 0 at multiples of pi n, whereas cos x equals 0 at pi over 2 or 90 degrees plus every 180 after that. So in this lesson, we're going to verify and prove more complex trig identities using the skills that we did last time, and then remembering the restrictions. So when you are proving an identity, some of the hints are as follows. Begin with the more complex side. Look at your reciprocal quotient and Pythagorean identity. Whenever you see a tan or a cotangent, rewrite it as a sine over cos. Actually, that is one of the suggestions. Change all of your trig ratios to be sines and coses. So if you have a secant, write it as a 1 over cos. If you have a tangent, write it as sine over cos. If you can, try to factor, if factoring helps. And if there's a sum or a difference of fractions, combine as a single fraction. And that can help. So as we were going through these proofs, ask questions if you need to. And proofs are something that they take some practice. They're creative because we don't necessarily all start at the same point for a proof. We might look at it from different spots. Okay, so I'll go through the first one with you, and then we'll see if you can go through the second one on your own. So it says, consider the statement 1 divided by cos x minus cos x equals sine x tan x. So it says, verify the statement is true if x equals pi over 3. So if I was to put this into my calculator, 1 over cos pi over 3 minus cos pi over 3 would be on the left-hand side. So what is cos pi over 3? So what does it equal? 1/2. So I get 1 divided by 1/2 minus 1/2. So what's 1 divided by 1/2? 2. And what's 2 minus 1/2? Good. So that's the left-hand side. Now I look at the right-hand side. So I have sine pi over 3 and tan pi over 3. So what is sine pi over 3?
3/2.
Good. And what's tan pi over 3?
√3.
Good. And if I take √3/2 and I multiply it by √3, what do I get?
3.
3/2, because the roots would cancel out. Okay. How could I use the graphing calculator to show that this is an identity? So how did I do the last one? How did I show the last one was an identity? What did I do on the previous pages? What did we graph here? We graphed sine x, which was the left side of the equation, and then we graphed the right side. So that's what I could do with this one, is I can let y1 be equal to the right-hand side of the equation, or sorry, left side, which would be 1 over cos x minus cos x. And then I could let y2 be equal to the right-hand side. And what am I looking for? If they are identities, what will I notice about my graphs?
They should be the same.
They should be the same. When I go to put this in the graphing calculator, I want to put brackets around this one. Bracket 1 divided by cos x, and then I'll have to close the bracket twice. And with this sine x, make sure you close the bracket around the x. So at this point in time, this verified it for the given value. This showed that in all likelihood the two graphs are identical, so it's probably an identity. However, I am restricted by the window settings that I put on my graphing calculator. And my graphing calculator is not great at showing me points of discontinuity. So it's probably an identity, but I haven't proved it's an identity. That's what I can do in step C. To prove it's an identity, we're going to prove that one side is equal to the other side. So I have, for my equation, so on the right side I have sine x tan x, and on the left side I have 1 over cos x minus cos x. Now one of the hints was to start with the more complex side. Don't restrict yourself to that. Start with what you know. So if I look at that, what could I do? So if I look at my formula sheet,
Can you change tan x to sine x?
okay? And then what would I do on that side if I was to keep going?
Multiply times at sine squared x.
So multiply them together. So I get this sine squared x over cos x. I can look on the formula sheet to see if there's anything else there, but really, once I get to something over something, one term over one term, it's probably not a lot that I can do more of. So now I can use this to kind of help me on the left-hand side. So when I have a fraction, that's being subtracted by something else. I want to combine it and write it as one term. So in order to subtract fractions, what do I need? Common denominator. So what do I have to multiply both sides, or sorry, what's my common denominator?
Cos x.
Cos x. So if I write everything over cos x, this first term's not going to change. It's going to stay as 1. But what do I have to multiply the second term by? And what does that give me?
Cos x squared.
Now 1 minus cos squared x, that's a hidden Pythagorean identity. The Pythagorean identity is the sine squared x plus cos squared x equals 1. And if I isolate sine, I get 1 minus cos. So I can rewrite this 1 minus cos as sine x, or sorry, sine squared x. So I now have shown that the right side equals the left side. These Pythagorean identities, again, we have to try to remember that they can come in different forms. So even though I see it written as sine plus cos, I have to remember that I can rewrite this as 1 minus cos or 1 minus sine. And it's like that, the 1 plus tan squared x equals secant squared x? Or is it 1 plus secant squared x equals tan squared x?
1 plus tan squared.
So the 1 plus tan squared x equals secant squared x, again, that can be arranged and written 2 other ways. So when you write your diploma and you get your formula sheet, I would circle that and I would put a note in there, reminder I can rearrange the formula. Or I would even rearrange it and write it in those other forms so that I have it to refer to. It doesn't take you very much time, and it's just one of those things where once you have it written out and you have it to refer to later on, just takes some of the stress off. Okay? Are there any restrictions? So in other words, are there any denominators? Do you see any denominators, Hannah?
Cos x.
Cos x. So what can't cos x equal? 0. So cos x cannot equal 0. And from the previous page, that means that x cannot equal pi over 2 plus multiples of pi n, where n again is an integer. Do I have any other different denominators? No. I have cos x on the other side. It's the same denominator. So that becomes my restriction. Okay? Okay, so let's take a moment and let's look at the next class example. We need to prove the identity algebraically and determine the non-permissible values. So on the left-hand side, I have sine x cos squared x plus sine cubed x. And on the right side, I have 1 over cosecant x. Where would you start at?
Can you factor out sine x on one side?
Sure. Let's take out a sine x. What does that leave me with?
Cos squared x plus sine squared x.
Okay. Now what?
Well, cos squared x plus sine squared x is 1.
Okay, so now I have sine x times 1, which equals what's cosecant x?
1 over sine.
1 over sine. So I get 1 over sine, which equals so I've now shown that the two sides are equal, so I can write left side equals right side. So now for my non-permissibles, I look for denominators. Where do I have a denominator? In your cosecant x, which is sine x. So sine x cannot equal 0. When does sine equal 0?
Multiples of pi.
Pardon me?
Multiples of pi.
Multiples of pi. Okay. Consider the identity sine A plus tan A over 1 plus cos A equals 1 over cotangent A. Which is going to be the harder side? Probably the left side. What can I do on the right-hand side? I have 1 over cotangent. What do I know about 1 over cotangent? It's going to equal tangent. So the right side is going to equal tan A. So that's really what I want to get to on the left-hand side if this is an identity. So what do I want to do with the tan A on this side? If I have, right, I want to change it to sine over cos. So I now have sine A plus sine A over cos A all over 1 plus cos A. That gives me this fraction to add. What would be my common denominator? Cos A. So if I write everything over cos A, what do I have to multiply sine A by? Cos A. So I get cos A sine A plus sine A on the top. And I have this 1 plus cos A as my original denominator. Okay? Now what?
Factor out sine A.
Can factor out a sine A. And when I factor out a sine A, what am I left with?
Cos A. Plus 1.
Plus 1. How do I divide fractions?
Multiply by its reciprocal.
Multiply by the reciprocal. Because what I have here is I have this fraction. And I can create a fraction down here by putting this over 1. So I multiply by the reciprocal, so the reciprocal becomes 1 over 1 plus cos A. Now what can I do?
Cross off cos A plus 1. Up and
Cos A plus 1, is that the same as 1 plus cos A? Yeah, because they're both positive. So I can cancel out these common expressions, which leaves me with sine over cos, which is equal to tan. Okay. Now, question B says, what are all the non-permissible values? So let's look at denominators. If we look, first of all, I've got this denominator right here, cos A. So cos A can't be equal to 0. Which means that A can't be equal to pi over 2 plus multiples of pi. What else do I have for denominators? I have right here, cotangent A can't equal 0. So if cotangent A can't equal 0, it implies that neither cos A or sine A can equal 0. So here's my new one. Sine A can't equal 0. So that means A can't be multiples of pi. Do I have anything else that can't equal 0?
Cos A can't be -1.
Cos A can't be equal to -1. Why not?
Because it has a denominator of 1 plus cos A.
Cos A equals -1. I'm going to get 1 plus -1. I'm going to get a 0 here. So this is where knowing your sketch of cos can be really useful. Cos equals -1 at pi. So again, A can't be multiples of pi. Or sorry, pi n plus every 2 pi. So it'll be at, this is at pi and then at 3 pi. But this right here, is that kind of included in this statement there? So I can write for my final is that A cannot equal pi over 2 plus multiples of pi and multiples of pi. And then n can't be, or n is an integer. So part C says show the non-permissible values on a graph of each side of the identity for the domain from 0 to 2 pi. So if I was to graph this, what would my graph look like? So take a moment and try graphing this. Your non-permissible values are happening at pi. So my window settings, use pi over 2 for your window settings. For my x scale. That will help. So it's kind of a weird looking graph, isn't it? Because you get these asymptotes that happen. So at 3 pi over 2, I have this asymptote. And at pi over 2, I have another one. At positive and negative. So I get these asymptotes that happen in the graph, and then I get a graph that looks like this. So for the graph of sine A plus tan A over 1 plus cos A, my non-permissibles are that cos A can't equal 0, and that cos A can't equal -1. Well, cos A can't equal 0 at pi over 2 plus multiples of pi n. So that's included right here. Those are those asymptotes. Cos A can't equal -1 at pi n and then every 2 pi after that. So that's right here. and right here is where I have these points of discontinuity. So those would come in as open circles. And then the graph ends up being recreated over here. The lines are all off, but that's okay. So in this graph, I have cotangent A, which is sine over cos, which means sine A can equal 0, and cos A can't equal 0. Well, cos A can't equal 0 at pi over 2 plus pi n. Those are the asymptotes. And then sine can't equal 0 at every pi. So every pi becomes this open circle, this one in the middle, plus these two on the ends. So every pi becomes an open circle. Okay? So last example. Secant squared x over secant squared x minus 1 equals cosecant squared x. Any thoughts of where to start at?
Your cosecant squared x, can you change it to 1 over sine squared x?
Okay,
I don't know if that helps.
so cosecant squared x is 1 over sine squared x. So that's the right side. So what can I do with the left side? And I'll give you the hint. Before you start rewriting all of the secants as 1 over cos, look at that denominator and look at what you have on your page. Do you have a Pythagorean identity that deals with secant? What is it, Rachel? Is it something like 1 plus, so 1 plus tan squared x equals secant squared x? Move the 1 over to the other side and what do you get? I get secant squared x minus 1. So I could replace this with tan x. So I could rewrite this as secant squared x over tan squared x. Which is going to be a lot simpler than rewriting secant squared x minus 1 as 1 over cos squared x minus 1 and then having to combine the fractions and going through all of those steps. So what is secant squared x? One over cos. And what is tan squared x? So if I divide the two fractions,
1 divided by sine squared x.
1 over sine squared x, which now equals the right-hand side. So the left side equals the right side. Do I have any non-permissible values? denominators? Do I have any denominators?
Well, sine squared x can't equal 0.
So sine squared x can equal 0, which means sine x can equal 0. We're not going to go through what the x values itself can equal. We're just going to see if we can identify which trig values, what they couldn't equal. So we have sine x. What else can equal 0?
Cos.
Cos, because I have cos right here as a denominator. So cos x can equal 0.
Tan x can equal 0.
Tan x can equal 0, which again then goes back into the sine or cos, so we've taken care of that. What about secant squared?
Co can't equal 1.
Can equal 1, which means that secant is the reciprocal of cos, which means that 1 over cos can't equal 1, which then means that cos can't equal 1. So we put this all together. We have that secant squared x can't equal 1, which means that 1 over cos x can't equal 1, which then means that cos x can't equal 1. Because if cosine x equals 1, then 1 over cos equals 1, which means secant. Can cos x equal negative 1? It equals negative 1 here. What does it equal here? 1 over negative 1. And what happens when I square it?
You get 1.
At positive 1. So can cos x equal negative 1? No. So cos x can't equal negative 1 either. That would be a standard of excellence type question listing the non-permissible values for this one. Specifically because this cos x equaling negative 1 would be something that most high school students, a large percentage, would not recognize. And it's because of working backwards. When that negative 1 gets squared, it now becomes 1 here. Okay? So your questions, question number 2 for A, C, and E.